We're going to start this video off with just a little bit of review from the last section, just one more practice problem. I'd like to evaluate and interpret a Riemann sum for f of x equals 1 minus x squared on the interval 1 to 4 with n equals 3 rectangles, and we will use a left Riemann sum here. So I'm going to start by drawing a picture of what this looks like. This is 1 minus x squared, so it's the graph of x squared flipped upside down and then shifted up by 1. So we would see something that looks like this. So we've shifted the vertex up by 1, and then afterwards it looks perhaps something like this. So here is 1 is going to intersect at 1, 1. You can verify that if you would like. And then we'll say here's 2, here's 3, here's 4, and then okay, there we go. So the first thing I want to do, actually let me just label these 1 and 4. First thing I need to do is calculate the width of my rectangles here. I should figure out how wide each of my subintervals is going to be. So I'm going to find delta x, which in this case is 4 minus 1 divided by 3. So I have 3 divided by 3, that's 1, and boy, that's just awfully convenient. So that means that each one of my rectangles will have width 1 unit long. And here something interesting is kind of happening. We actually don't have, we'll talk about that later. So think about what makes this problem, I guess, different from the example we looked at in the last section. Just keep that in the back of your mind. What makes this one different? So I want to use a left Riemann sum, so I'm going to split this up into 3 rectangles. I've already said here are my subintervals. I've got 1, here's 2, here's 3, and then there's 4. So 1, 2, 3, 4. So first up, I'm going to look at the interval between 1 and 2. We're doing a left Riemann sum, and this one's kind of weird. It's a little bit interesting because we say, okay, here's the subinterval that we're going to look at. We want to use 1 because that's the left endpoint. So we'll say, what's the height of my function at 1? Well, it's 0. Technically, I don't really have a rectangle. I have a line. If you're unsure about that too, we can always say, okay, if I want to calculate the area of that first rectangle, take the width of that rectangle, which is delta x, times the height of my rectangle, which, remember, the function that we're working with here is f of x equals 1 minus x squared. We said we are going to use 1 to determine the height of our rectangle, so delta x times f of 1. So delta x is 1 times f of 1, that's 1 minus 1 squared. I have 1 times 0, which gives me 0. So I have an area of 0. And hopefully that makes sense because we don't really have a rectangle. If anything, I suppose we just have a line. But okay, that's fine. We'll just move on to the next subinterval. So now we're going to look at between 2 and 3. Again, we're doing a left Riemann sum. So here we have 2. So we have delta x, and actually let's draw in our rectangle first. Let's draw in. So this one's a little bit different. The reason I wanted you to think about it is look how our rectangle is oriented. It's below the x-axis now. That's kind of interesting. I wonder what that's going to do to our Riemann sum. So we're looking at calculating the area of that rectangle, which is delta x times the height of my rectangle the height of my function at 2, so times f of 2. So I'll have 1 times 1 minus 2 squared. This is 1 times negative 3. Look at that. I ended up with negative 3. I don't want to worry about that too much, though. We're going to come back and talk about why this is negative later on. But let's continue on. I have one more interval to look at. I want to look at the area between 3 and 4. We're doing a left sum, so we're going to use the height of our function at 3. So it would look something like this. And we're saying, okay, we're going to find this area right here. We said we're using the height of our function at 3, so we want delta x times f of 3. So this is 1 times 1 minus 3 squared, which is 1 times negative 8 gives me negative 8. So if I wanted to calculate the area, this Riemann sum here, I would say 0 plus negative 3 plus negative 8, I have negative 11. So this is the value of my Riemann sum. You might be saying, well, hold on there, Mr. H. Why is it okay that we ended up with a negative value? What's going on there? Well, the reason this is happening, the reason that this is happening is because these rectangles that we drew fall below the x-axis. That's why I ended up with a negative value. And if you look at the region that I'm trying to estimate here, I'm going to shade in the whole region that I'm trying to estimate. I'm trying to estimate this yellow shaded region. That yellow shaded region falls below the x-axis. So this is something that will happen with Riemann sums if we have a negative Riemann sum. Most of our area is actually below the x-axis. So our Riemann sums are going to count area below the x-axis as negative. So if we have essentially, if we have a positive area, and we're just going to think about one region for right now. If we're working with a positive area, then we're talking about area above the x-axis. And if we have negative area, generally we're talking about area below the x-axis. And here we have this definition. It says, let R be a region bounded by a continuous function f of x over the x-axis over a to b. The net area of R is the sum of the areas of the parts of R that lie above the x-axis minus the area of the parts of R that lie below the x-axis. So we're just saying here that we're counting the area above the x-axis as positive. We're counting area below the x-axis is negative. So what that means is if I wanted to look at some function, and let me just draw in some function. Let's say my function looks like this. And let's say I had a way to know the exact area. I knew that the area right here, let's say that is 5, and I know that this area over here is 3. If I went and wanted to find the net area, which is what the Riemann sum calculates. If I wanted to find the net area, I would take the area above the x-axis, which is 5, and subtract the area below the x-axis, which is 3. My net area would be 2. If you see a problem talk about total area, on the other hand, I don't know that our textbook gets into total area, then it would count all area as positive. So if we wanted total area, we would have 5 plus 3 would be 8. So this is a big difference between net area and total area. If you see an example that just says area, it doesn't specify whether it's net or total area, we are talking about net area. So if they don't specify, if they just say find the area bounded by the curve in the x-axis, then we're talking about net area in that case. So we're going to try and start to put some of these ideas together that we've been talking about. We've been talking a lot about Riemann sums, and the important thing about Riemann sums is that they give us an approximation of the area under the curve, but it doesn't give us an exact area under the curve. We did figure this out in the last section, though. We said the more rectangles we use, the smaller our error gets. So if we have more rectangles, we have a better approximation. The problem that we're going to run into, though, is if we have any finite number of rectangles, we still have error. Error. Which is bad. That's kind of, we would prefer to not have any error, because at the end of the day, right, we want to be able to say this is the area under the curve. This isn't about the area under the curve. This is what the area under the curve is. So any finite number of rectangles is just not going to do. And hopefully you see where I'm going with this. I said specifically a finite number. What if I didn't use a finite number? What if I used infinitely many rectangles? We would need infinitely many rectangles in order to get a perfect approximation, because then at that point it's not even really an approximation anymore. It's just that's the area under the curve. We need infinitely many rectangles, which I think is kind of an astounding idea here. So what this Riemann sum business, what we're trying to do here is we're trying to say, actually, okay, if we want to make our estimate perfect, we have to use more and more and more and more rectangles. No finite number will do. We can't use 10,000, we can't use 10 million, we can't use 10 billion. It's still going to leave us with error. But if we use infinitely many rectangles, if we just keep adding more rectangles, eventually we'll get a better and better and better approximation until we have a perfect approximation with infinitely many rectangles. So if I want to calculate net area, I've got this funky looking guy down here, and I want to pull this apart here. This part should look familiar, this part that I've circled here. It says f of x sub k star times delta x. So this piece right here is saying, okay, I'm going to calculate the area of my rectangle. And that's what we were actually doing in our Riemann sums above. Here's the height times the base on every single one of these. We switched the order around, but the order is not particularly important here. So I'm going to take the height times the base of every single one of these rectangles. This funky looking symbol right here is called a sigma notation. We didn't really have a chance to get into sigma notation in the last section, but essentially a sigma notation is a way to show a summation in a very small way. It's kind of a compact way. So really what this says is I'm going to repeat this process of finding height times the base n number of times, and then I add all the results together. And that's exactly what we were doing in the last section. We only did it with, say, n equals 4 or n equals 3, right? But I could extrapolate that and I could do n equals 100, right? It would be kind of a pain, but we could do it. It wouldn't be fun, but it's possible, yes. So we find the area of n rectangles, we add them all up, and then if I want the perfect approximation, if I want the exact net area, I say, oh no finite number of rectangles will do. We can't just say to n. We have to look at now, hey, look at this, the limit making a comeback. This is so exciting. I want to look at the limit as this n approaches infinity. If we look at that limit, that will tell us our net area. This is pretty freaking cool. So what we're going to do essentially is when we find area under the curve, we are essentially finding the area of infinitely many rectangles and then adding them up. I cannot overstate how cool I think that is. We're going to add together infinitely many rectangles and then end up with a finite result. That is pretty sweet. But we should talk about what this means for us going forward now. We're going to use this idea of net area to define something called the definite integral. It says a function f defined on the closed interval a to b is integrable, so that just means we can integrate it, on a to b if this net area exists. And this is a slightly different way to write the net area here. I prefer to think about it as the number of rectangles is getting larger and larger and larger. We're using more and more rectangles, but another way you can think about it is that the width of each one of those rectangles is getting smaller and smaller and smaller. The width is getting infinitely small. But you can think about this piece right here. If the net area exists and is unique over all partitions of AB, and all choices of x sub k star on a partition. This part right here, over all partitions and all choices of x sub k star, that's not really particularly important for us. We talked about regular partitions, but that's not the only way you can partition something. You can partition it however you like. But this is saying if you make those partitions small enough, you're going to end up with the same number every single time. You're going to end up with a unique number. This limit is the definite integral of f from a to b, which we're going to write as this. So the integral from a to b of f of x dx is equal to the limit as delta approaches 0, f of x sub k star times delta x sub k. So again, here, this is just a net area. So when we think about the definite integral from a to b of f of x dx, right now, we don't necessarily know how to even find this value, but we know what it represents. This represents the net area bounded by our curve and the x-axis. So this is going to be this thing that we're chasing, this thing that we're trying to find here in the next few sections. In this section and the next one, we really like to be able to come up with a way that we can evaluate this definite integral, this thing that tells us the net area. Some terminology that we need to talk about here. A and B are called the limits of integration. So A is called our lower limit of integration. B is called our upper limit of integration. That squiggly line that we talked about a little bit way back in 4.9, that is called an integral. The function that is inside of that integral is called the integrand. So that's the piece that we're actually integrating. And again, that dx, that's the differential. That tells us our variable of integration is x. So what that really represents is this width. It's actually saying this width is actually getting infinitely small. So as the width of our rectangles gets infinitely small, then we approach our actual net area. But for right now, just know that dx tells us that we're working with the variable x. Next, we have a theorem. It says if f is continuous, so as long as we're continuous, or bounded on a to b with a finite number of discontinuities. So either 1, it's continuous. If it's continuous, it's fine. Or 2, if it's bounded on that closed interval, which when we say bounded, that means there's some number, and I'll draw it down here. There's some number that we don't get higher than. So here, this is a bounded function, right? We're bounded by this dashed line. But if I drew something that, say, had a vertical asymptote, if we were looking, say, from here to here, we said we had a vertical asymptote right there, this is not a bounded function because I can't say, well, my function doesn't get any higher than this because it passes that point right there. So if it's bounded and with a finite number of discontinuities. So you're allowed to be discontinuous as long as you only have a finite number of discontinuities or are bounded. If one of these two cases are hold, either we're continuous or we're bounded with a finite number of discontinuities, then we get to say f is integrable on AB. So that just means the net area exists. We can calculate the net area. The last thing I'd like to do to wrap up this section is just to kind of see the relationship between Riemann sums and definite integrals here. So here I actually have this Riemann sum. We haven't used this notation, but I just want you to see it at least once just to say, hey, yeah, I've seen that. This piece right here, so if I look at this, here's my sum, and I'm summing so that the width of each one of these rectangles gets smaller and smaller and smaller. So this is what tells me, okay, we're working with a definite integral. So we have our integral. Our limits of integration are 0 to 2. So 0 to 2. This piece right here, this 4 minus x sub k star squared, this is actually our function. This is our integrand. So we're integrating 4 minus x squared. And then the delta x is kind of covered up here. The delta x right there, that is our differential dx. What's happening is that this width is getting smaller and smaller and smaller until we say, you know what, it's infinitely small. And that's actually what that dx represents, is it represents an infinitely small width of a rectangle, which we need to have infinitely many rectangles. So if I wanted to express this Riemann sum as a definite integral, this is what I would be looking at here. We won't see too many problems, and I don't want to focus too much on Riemann sums. We're mostly going to focus on, okay, how can we find and evaluate this idea of net area? Because that's where I'd like to go. I'd like to be able to say, okay, I have this idea, this definite integral. I know what it tells me. I know that it tells me the net area, but I don't know how to find it yet. And that's what we're going to start to explore in the next few videos of this section.